Okay, thank you. Welcome back to the second day of CTNT. So I will continue to talk about p-adic functions, on ZP. So lecture 2. So today we're gonna. So yesterday we talked about, just give a brief introduction of what p-adic integers are. Namely, ZP is a collection of them as completion of the integers with respect to the p-adic norms. So today we're gonna talk about. So towards the end, we talked about sort of making Z a metric space with the p-adic metric, and then try to complete it. So today we're going to spend some time to talk about, first of all, the Cauchy sequences in ZP, and then, give you a picture of what ZP looks like, and talk a little bit about the topology of it. And then towards the end, I'll talk about exponential functions, logarithmic functions on ZP, which is kind of something really cool if you haven't seen them before. And then I'm going to use this. Discussion of exponential and logarithm functions to explain the structure of ZP cross, namely invertible functions on ZP. So this is all the elements in here. A is invertible, or okay, fine. Exists a B in ZP such that A B equals 1. Anyway, so, all the elements that are invertible multiplicatively. So let's first of all recall. Overall, you hear me fine, right? Overall, you hear me fine, right?
Yeah, it's all good. Thank you.
It's all good. Thanks. Just want to make sure, because yesterday there's some breakup. Okay, so let's first of all recall that ZP is a completion of Z with respect to a p-adic norm. What that is that if my n is exactly divided by p to the beta's power, so namely if you look at sort of the factorization of n and see how many prime number p there are, so there are beta of them, then I say, okay, the p-adic evaluation of n is exactly this beta that exactly divides n that many times, and then the p-adic norm is 1 over p to the beta, so it's usually less than 1. The first theorem we talked about is that the p-adic norm defines a natural metric space structure on Z. That's to say that if I have two integers, x and y, then I can define their p-adic distance to be, it takes the difference of x minus y, and then you take the absolute value. So the p-adic absolute value we define over here. Basically, look at how many times that this number is divided by p, the power over p, and then take 1 over that, like 1 over that. Okay, so then ZP is the completion of the range of integers, or like the set of integers with respect to this p-adic metric. And namely, if you know what completion means, it's just basically ZP is a bunch of sort of Cauchy equivalent classes of Cauchy sequences. Right. So, excuse me. This theorem is not. There's a little bit to say about this theorem. I'll talk about what goes into somehow proving the theorem in a bit. But let's admit the theorem, and I will first of all give you some sense of, or give you a sort of better understanding of what ZP looks like, and what this sort of p-adic metric look like before actually going into the proof. But before that, let's sort of talk a little bit about what we also just reveal what we talked about last time. We also said that last time if A is an integer and P does not divide A, then this A is invertible in ZP. Namely, you can find another p-adic integer B such that A times B is 1. You can actually extend this argument a little bit to A in ZP, and such that P does not divide A, in the sense that when you write down A equals A0 plus A1 P plus A2 P squared, and go on so forth, this A is not 0. So that's what I mean by P does not divide A. Just like what happens for the integers when you expand it like this. But for integers, of course, you expand it in a finite level, but here you expand infinitely. And this is also equivalent to, I can also sort of extend the p-adic evaluation here to the ZP. So let's just say the p-adic evaluation of A is 0. And just like happening for integers, if P does not divide A for a p-adic number, this A is also invertible. The same argument we proved for this works the same way. So here's a corollary of this theorem, which is that ZP is a PID. And of course, a range of integers is also a PID. But what's different is that a range of integers have many sort of maximal ideals, one for each prime. But ZP, there's a unique maximum ideal, namely the ideal generated by P. So that's something very interesting about the ZP in the sense that, when we talk about sort of integers and rational numbers, one thing we know is there are many, many primes. And somehow, philosophically, when you work with number theoretical questions, one of the things that you have to sort of handle all these primes at the same time. But this ZP provides you a way to, in some sense, amplify just one prime P. So there's a general philosophy that if you want to solve some sort of number theoretical question about the integers or rational numbers, there might be a way. Sometimes there's a way to do it in 2 steps. Namely, first of all, you do a sort of similar question over ZP, where this particular prime P is sort of signified. And then you try to group together all these sort of information about different ZP of different P's together, and then try to get information about Z. So that's sort of a general philosophy in number theory to attack a sort of more difficult question. Right. So the ZP has very, so as you see, that's the PID, and then there's a unique maximum ideal P. And from this, I can just simply define the QP, which is just fractionalized, the ring of fractions of ZP. And it turns out all you need to do is just invert the prime number P to make a field. Or if you want to make it sort of explicit, because every p-adic integer in ZP can be written as in sort of a power, sort of this P power series. So what you can do is that you can write, okay, but then of course if you do QP, then you have to invert, you have to have P in the denominator. So you can simply write elements in this as, maybe I just write it like this. So a minus n P to the minus n plus a minus n plus 1 P to the minus n plus 1 for some a, I guess for some n, and a all ai in 0 P minus 1. So this looks very much like the p-adic integers over here, except that you allow some sort of it looks like sort of finite. If you think of this sort of really power series where P is kind of indeterminate, this is something, with a sort of pole. But of course, P is a number, so you really don't talk about pole or P is a number, but it just allows some denominators, I guess. And if you look at this, if you look at the way you express this, I guess ZP are the ones where somehow this a minus, or maybe just sort of, let me just write formula like this. So this is, if this is the a, that's all the sort of negative coefficients are all 0. That's what ZP inside of that is. And also I want to point it out that somehow as we know that this Z sits inside P, ZP, and because of the, and every, maybe just, and every integer that's not divisible by a is already invertible in ZP. So Q is basically coming from the ring of integers by inverting P and other numbers. But all the not multiples of P are already inverted in ZP. So therefore, if you invert this P here in ZP, then this Q must be contained in QP. And here's some. So therefore, this QP indeed is we'll see in a bit. Okay, so you have this, and I can actually. Sorry, a little lost myself. Okay, so here's some obvious fact about. So I wanna maybe somehow make a claim of this first. Excuse me. Here's another sort of statement that this QP is actually a completion of Q with respect to the p-adic metric as well. But for this, I have to somehow explain a little bit, because earlier on we only talk about the p-adic evaluation, like here for integers. So I have to extend it to the rational numbers. So So we make a little bit. Let's make some observation. I have some trouble with this. Hold on a sec. The page. There we go. Out of space here. So let's note. I have to first of all extend the p-adic metric to all of Q. So first of all, note that for n and m integers, if I take p-adic evaluation for m, n times m times n maybe. So what is this? So what is p-adic evaluation of a number? It's just how many times is divided by a power of p. How many times is divided by a p? So of course, if m is divided by vpm times, and then n is divided by vpn times, then you'll take their product is divided by sum of that many times. So if the valuation goes as additively, then m times n, the p-adic evaluation, p-adic norm is p to the negative power of this valuation, which is p to the negative valuation this, which is basically m p times. So this looks very much like the real case when you have to take absolute value of the product of two numbers. It's just product of absolute values. In fact, this works definitely for z, and by continuity, it works also for zp. So now with this multiplicativity, I can extend the p-adic evaluation and this norm to Q. And of course, once I'm done that, I can extend it to QP as the following. So if I have a number, a rational number, a mod b. So I mean, I just define to be p-adic evaluation of a minus p-adic evaluation of b. Basically, I define it so that this type of thing also works over Q. And also, that, or even like if you think about this really makes sense. If that many power of p divides a, and that some other number of p divides b, then the total thing divided by the number of p is this a over b is divided by p is should be the difference in some sense. And of course, this expression does not depend on how you write your rational number as a over b. You can if you have another way to write it, for example, times r here, and this will be, and somehow the first term will be at, maybe let's do this. So yeah, so suppose you rewrite this as times r here. Then what's going to happen? The first term will get a p-adic evaluation of r, and then the next term will also give a p-adic evaluation of r, and then these two will cancel each other. So maybe here's an example. If p equals 5, then 5 adic evaluation of, for example, 7 mod 15 is basically ignore all these sort of prime to 5 factors. So this is p-adic 5 adic evaluation of 7 minus 5 adic evaluation of 15, 0 minus 1, which is negative 1. And also you can extend the norm in the same way. So that's just the norm of A, norm of B. And with respect to so-defined norm, the QP is the completion of Q with respect to this p-adic metric. Okay. So now I want to draw a picture of what ZP and QP looks like under the p-adic metric. So as I said last time, this sort of the p-adic world is very, very different from the real world. So there's no really good way to draw them nicely, but there's some way to illustrate what's happening. So let me try. So let's try p equals 5.
Liang?
Yes?
There is a question. How do you extend the p-adic norm to ZP?
Very good question. Maybe I should say it. Yes. So how to extend p-adic evaluation and norm to ZP. So if I have a p-adic number, say, let me just write down a number. So 3 times p to the 4th plus 5. I mean, of course, p is at least 7. Plus 8 times p 6. So I want to know what's the p-adic evaluation of this. Well, you see how many times this is divided by p? That's 4 times, because the lowest exponent is 4. So therefore, p-adic evaluation of this is just 4. And the norm of this, of course, is just 1 over p to the 4th power. And another way to say, I also said something like by continuation. That's because somehow you think of this as, you think of this way, the way I wrote this is as the limit 3 times p to the 4, 3 times p to the 4 plus 5 times p to the 5. And then, 3 terms. So maybe p greater than 711, so that 8 doesn't get in the way. So you see that what's the p-adic value of this one? It's just 1. And this one is also 1. This one is also 1. In some sense, one thing you know is that this p-adic, once you will see that this p-adic value will be
4. Do you mean 4? Do you mean 4? The valuation
yeah, absolutely. Sorry about that. 4. Yes. So yeah. So in this limit, you will see that this sort of stabilizes. Or maybe it started out with 0. So at the beginning, the p-adic value is infinity, but then it will stabilize as you somehow change by little. This is sort of the norm side. The side of the norm is turns out to be stabilized after a little while. We're gonna see that as well later. Does it answer your question? Okay, sounds good. I'll move on to, I guess, talk about ZP and QP. Are there more questions before that, actually? Okay, I can't really see. Okay, sounds good. I'll move on. Okay, so let's put, it doesn't matter because I'm going to draw a pentagon, so I put 0 here. So this is 0, and where is 1? Well, we know the distance between 0 and 1 is, this distance is 1. Okay, so that's where 1 is. Okay, 2 is here. Let's put 2 here. The distance is also 1 because 2 minus 1, you take the p-adic norm. It's also 1. But what about 0 and 2? Well, 0 and 2 is equal. You're taking the 5-adic norm of 2. Of course, this is also 1 because 2 is not divided by 5. I should draw a regular triangle, but you will see that I have 2 more points, 3 and 4, and the distance between each one of them, they're all distance 1. And any pair you see here, their distance is 1 because their differences are not divided by 5. Okay. Now, what gets interesting is get to 5, the number 5. So what about 5? The distance between 5 and 0 is quite small, actually. Because if you take the 5-adic norm of this one, this is 1 over 5. So this is 1 over 5. Okay. And where's 6? And also, what about the distance between 1 and 5? That's also 1. Because this difference between, that's basically norm of 4, which is 1. And what about 6? 6 is going to be somewhere very close to 1 because the difference is 5. So 6 is here. And you can kind of get the pattern. And 7 is something very close to 2, and then 8 is here, and 9 is here. So you already kind of see that this is not something you can draw very well on a piece of paper because already see the pentagon, like all the sides, like all the distance between all these points should be 1. There's no way to draw regular triangles this way. But anyhow, I think this is a good enough illustration. So let's continue this. What about 10? Well, 10 has the same distance to 0 and 5. Again, 10 to like this 1. Let me just excuse me. The distance between 10 and this 1, 2, 3, 4, they all have distance 1. And you can sort of continue this game. So this is 11 is here, and so on and so forth. You kind of see circling, start to circle. And now let's focus a little bit on this sort of circle around 0. I have 5, 10, and the next thing is 15. Okay, and then I have the 20. Maybe let's sort of draw a small circle here. You can think of this as a smaller stellar system that's sort of circling around 0. And after 20, there's another thing called 25, another number called 25. That's even closer to 0. This is 1 over 25. And of the same sort of status, there's 50, which is also very close to 0. Let me see. Same distance. So you can see there's a smaller circle around 0. And in the same way, there's going to be a small circle around 5 in the sense that this is 30, which is 5 plus 25. And you can also say this is 55, which is 5 plus 50. This is like 1 over 25 as well. And around each of these sort of small circles, small sort of point or small things around this, you have the small orbits here. And you can even have like 125, and there's no, I can't draw this very well. So there's a 125 inside, there's an even smaller thing orbiting around 0. That's 125 and then 250 and so on and so forth. And in a similar way, around 1, you have sort of a similar picture. You have in some sense, a bunch of numbers whose distance to that is 1 over 5, and then you have distance is 1 over 25, and each of 6 and 11, you have these sort of small circles. And the sort of same pattern applies to 2, 7, also applies to 2, applies to over here, you would have some sort of thing, sort of these things here, and also some sort of these things here as well, and these things here as well. So that's roughly what ZP looks like. Okay. Let's see. And then you can ask, what about QP? Well, QP. Well, these are all sort of integers. Oh, maybe I should also say, what about the sort of transcendental number, or sort of like actual Z elements in Z5? So say I want a 1 plus 3 times 5 plus 5 times, oh, not 5 times, excuse me, 2 times 5 squared, and then so on and so forth. And where's that going to be? Well, if you think about it, so first of all, you kind of start with near 1, because this is 1 here, and then go to 3 times 5. You're going to find where, let me just say this, assume this is 16. So basically, you're kind of moving on this sort of picture as you start with 1, and then you move to 16, and the next one is at 50. So 50 is say here, so this is like 66. Just try to move here, and then you somehow move very like change by just a little bit on this picture, and then somehow the limit will be your p-Adic number as written here. Okay. And now, so this looks very much like fractals. Think about it. So this is how like number theory thinks of fractals. See, we already know this. Just kidding. Okay. So what about? So this is what ZP looks like. So all this picture is now ZP. So ask, what about QP? So for QP, how should I put this? We have to zoom out a little. Let's try to do this. This is the benefit of having a long online lecture. So I can zoom out. Now I have another number called 1 over 5. So remember, this is a 0. The distance between 1 over 5 and 0 is actually 5. Because this is a little counterintuitive, but really this is sort of the sort of p-Adic norm. But we know that p-Adic norm is 1, but the p-Adic norm of 5 is 1 over 5. So the distance is 5. So we have 1 over 5 here. And similarly, I have something called 2 over 5. I have something called 3 over 5. I have something called 4 over 5. The distance between each one of them, I should draw a bigger sort of pentagon, but anyways, the distance between each one of them is 5. And near each point of these vertices, I would have sort of a similar sort of pentagon like what we have over here. I would have the same thing over here. What this corresponds to, for example, this one, what this pentagon corresponds to is that somehow these vertices are like sort of 1 over 5 plus 1, and 1 over 5 plus 2, and so on and so forth. And this sort of 1/25, you want to do that, you have to zoom out further. And maybe I'll just do that just very briefly. You have to somehow, again, zoom out further and then do a 1/25 very far away. So that distance is 25, and so on and so forth. In some sense, QP is, you should think of it as kind of a fractal in both ways. Zooming, like getting very, very small and going out very, very large as well. Okay, so now, but later purpose, let me sort of, I'm gonna need this picture here, so I'm gonna forget about these big ones. So I need this picture to talk a little bit about the structure of ZP and QP as well. So, okay. So what am I gonna do? I'm gonna sort of maybe take this picture. So I have this piece here. What is this? This is, let me just write it over here. What is this? If you see what's happening here, that's like which point that's happening in the things I circled here. All the points in here I circled are of the form 1 plus 5z5. In the sense that this is all the elements which are distant to 1 is less than or equal to 1/5. Right? But then if you think about it, the way I define this is also the same as 6. Oh, maybe I should say this is all the elements in, let me say, Q5. Somehow norm of a minus 1 is less than or equal to 1/5. But I want to say this is also the same as any other number in here, say 6, that define the same thing. Well, why is that? That's because, well, one way to see this is that somehow you can write the 6 plus this as 1 plus 5 plus 5z5, right? So what 5z5 is, you know, is 5 times something. So like, you know, if, so maybe we write it like this. So if it's 6 plus 5x, then this would be the same as 1 plus 5x plus 1. So this belongs here. Okay. And maybe I should also explain why 1 plus 5 can be described this way. So let's do that. So let's see. So for a in Q5, if I want a minus 1, the 5-adic number is less than or equal to 1/5. That's to say, how should I put this? That's to say, let's see. Maybe do it this way. Times 5 gives me 5 less than or equal to 1. But I can reinterpret 5 as norm of 1/5. And this all together by multiplicativity. You have many ways to say this. Let's just sort of do it this way. This is a minus 1/5. 5-adic norm less than or equal to 1. But we already talked about, I think we already talked about, okay, let me just move up here. Where is this? We talked about over here that, I thought I talked about it. Maybe I'll somehow just use this here, because ZP inside QP are the elements where this negative powers is less than is equal to 1. So really, what's happening at ZP is all the elements A in QP, where the norm of a p-Adic norm is less than or equal to 1. And therefore, if you admit that, this will tell you that a minus 1/5 is actually in Z5. So rewrite this as a is in 1 plus 5Z5. Okay. Right. So I probably won't have time to prove it over here. I'll just move it down here. Okay. So let me say a little bit about this. So what about the topology of this ZP? So here's, actually, you know what? Before that, let me stop to see if there's any questions about this picture of ZP. So Alvaro, you're still with me, right?
Yeah, I'm here. There is a question. What would be an element in ZP but not Z? What's an element that is a p-adic but not an integer?
For example, I guess. Well, that's not an integer. For example, you can do like 1 plus p squared. Keep going. That's just 1 over 1 minus p. That's a rational number, not a integer. And in fact, in one of the exercise I posted yesterday, you can show that there's a question of, I guess, any rational number. You know, if you do like 1 over something, any rational number where there's no denominator, there's no p in the denominator, can be expanded as a p-adic integer like that. Any rational number, if you expand it in the sort of power, like looks like power series like this, and the coefficient in front of the powers of p's, if you start with a rational number, these coefficients are periodic and converge every sort of rather periodic after certain steps. And any sort of essentially periodic ones are rational numbers. Just like what we know for, let me just sort this a side question just to answer that. So if you start with, you can start with a0 plus a1p, for finite terms, and then you add sort of some periodic terms like p to the n plus 1 to the p to the n plus r with some sort of a and b, and then you start again, a p to the n plus r plus 1, p n plus 2r, and then you do another one. So these type of numbers correspond precisely to rational numbers with no p in the denominator. It's one of the. This looks very much like sort of a periodic decimal expansions correspond rational numbers, and the proof of these two are very much the same. Other questions or comments?
No, it seems you're okay now.
Okay, sounds good. So moving on to topology. So I want to say that each of the disk like this of ZP and QP, each of the disk like this I just draw is open. Or more generally, of the form a plus p to the n ZP is open. And because of this, actually each one of them is open and at the same time. Closed. So in fact, QP and ZP are very, it's not a mathematical word, are very, very disconnected. In the sense that somehow each of these disks here, they're different kinetic components. And even inside of each of the disks here, these smaller disks you have here, they're also disconnected from each other. And these sort of even smaller disks are also disconnected from each other. So somehow the topology is very, in a sense, disconnected. It's very sort of different from our experience. Nonetheless, here's the fact. It takes a bit of time to prove, but anyways, this is ZP is compact and Hausdorff. So those are basically sort of basic properties of ZP. Let me spend a little bit of time to go back to earlier our theorem here. Let me sort of maybe copy and paste. Copy. I want to say a little bit about this. There's a little bit to prove about this, because we need to check something. It doesn't really come for free. I need to check this dxy. You want to show something to define the metric space. I want to say that, okay, if the distance 2 points, you need to check if distance between 2 points is 0, then x equals y. But this is okay because the distance is just x minus y norm p, and this is a norm because so therefore if the norm is 0, then they're the same. So that's okay. But then the other thing is the triangle inequality. This is something we have to check. But in fact, we have a stronger triangle inequality. That's a key feature of the p-Adic analysis. Not only you have a triangle inequality, you have a stronger triangle inequality in the sense that dxz is not only less than equal to the sum of the two distances between x and y and z, it's less than equal to the maximum one of them. In fact, you can show that. I probably won't have time to actually prove this. Maybe I'll just briefly indicate this, is that all triangles are isosceles. It's a very strange phenomenon in p-Adic world, is that all the triangles you draw are actually isosceles. Namely, the two sides, two of the three sides are equal. Okay, let's come back to prove this triangle inequality. So what this means is to say that x minus this less than equal to max of x minus y, y minus z, p. So maybe let's set a to be x minus y and then b to be y minus z. So let's sort of, again, that's equivalent to say norm of a plus b. That's equal to max of norm of a, norm of b. So let's translate to something that I'm more familiar with, called valuations. So it turns out in the p-Adic world is sometimes more, I guess, when you work with p-Adic things more, the p-Adic valuations are easier to work with than norms, I guess. So what I said here is the sum of the p-Adic norm of the sum is less than equal to the bigger one of the p-Adic norms. It's equivalent to say the p-Adic valuation of the sum is greater than or equal to the minimum of the p-Adic valuation of the two of them. The reason is that basically you see that there's a change of inequality then turning max into mean. That's because if you look at how these two are related, this is sort of a strictly decreasing function. So therefore, when you change from one to the other, you change the inequality and then change max to mean. Then how do you prove this? Show that the p-Adic valuation of a plus b is greater than or equal to the smaller one. Well, let me just sort of say what it really entails. It basically says that if we know some sort of p to the n exactly divide a, and then p to the m exactly divides b, then p to the smaller one of the a, m, and n must divide a plus b. That's basically what it says. So if you think about it, the right hand side is, this is how many powers of p would divide a. This is how many powers of p would divide b. And you want to say that the number of powers of p that divide a plus b is at least that much. So that's to say, if p to the n divides a and p to b divides b, then the smaller power would definitely divide a plus b. But this is sort of obvious, right? I mean, if m is greater than or equal to n, then of course p. We should say without loss of generality, I can say m is bigger than n, and therefore p to the n will definitely divide b, and therefore putting these two together, you get p to the n divide a plus b. So you're done. So basically, this looks like sort of a fancy. So all this says is somehow all we're doing is just sort of a fancy way of saying this sort of simple fact about divisibility, but we kind of interpret it in terms of a stronger triangle inequality, and use this to define a metric on Z and do a completion to get something that's somehow interesting to work with, I guess. Right. Are there any questions about this proof of this sort of stronger triangle inequality? So this is a key difference. This stronger triangle inequality is a key difference between the p-Adics and the real one, as we explore this fact in a bit. Okay. So let's talk about the correlate of this stronger triangle inequality. That's somehow the difference between p-adic analysis, so-called p-adic analysis, and the real analysis. So if I take sort of infinite sum like this, if I take an infinite sum, like x1 plus x2 and go on, where all the x's are zp, and I want it to be absolute converge, because otherwise the sum won't make sense. The point I say, okay, I only need the limit of this norm to be 0. But so what's the difference between the real story and this one? For the real story, so the real story really need a limit of 2x and m and n, the difference to be 0. In the sense, if you were the one to say is the correct way is for any epsilon bigger than 0, you can find an n such that for every n and m greater than or equal to the capital N, this distance is less than epsilon. But in the p-adic world, I don't need sort of two integers n and m. I just need sort of this xn here. Right? Oh, sorry. I'm writing it. My bad. Writing this as sequence form. My bad. So I really need. My bad. Excuse me. Sorry. I'm really writing as in the sequence sense. I want to sort of the partial sum, like a whole sequence of things when you sum together. That thing goes to 0. But in the p-adic, all I just need is for every single term, the norm goes to 0. So why is that? So here's a proof. Of course, we know that the real story is always the correct story in the sense that if your Cauchy sequence satisfies this condition, then it converges. Now I want to show that in the p-adic world, as long as you guarantee that the norm of the single term goes to 0, then the Cauchy criterion holds. So that means that if you have, so again, sort of like, let's sort of do this thing more rigorously. For any epsilon 0, and I can find the n such that when n is bigger than n, I have norm of this is less than epsilon. So now I have absolute value of, I should say for any m bigger than n bigger than n. I consider this sort of the partial sum like this, the p-adic norm. But by this strong triangle inequality, what we had earlier, maybe in particular this form here, the norm of a plus p-adic norm of a is less than or equal to the maximum of the two summand. So I can generalize it to n times, so multiple times. So really, this is not less than or equal to the sum of the norms, but only less than or equal to the maximum of this norms. But each individual one is less than or equal to epsilon, so this is less than or equal to epsilon. We're done. So here's maybe a kind of a slogan. Is that sequences are easier to converge. Sorry. I don't know why. In p-adic topology. So p-adic analysis are, I should say, probably easier than the usual real analysis in some case. So now I'm going to take advantage of this. Maybe I should stop here. And are there any questions about this? Okay, moving on. So I'm going to take advantage of this and talk about construct some sort of cool functions. Let's see. I want to talk about exponential functions, xp. I want to say this makes sense in ZP. So what do you mean by exponentials? I mean, there's no real, there's no e, like 2.718 blah blah blah. But in the real analysis, what is exponential of x really? We have the Taylor expansion, right? And I want to do the same thing. Of course, there's no sort of e, but then the Taylor expansion somehow, I want to say the Taylor expansion really makes sense. Let's say this makes sense. So why is that? So again, basically, I want to show this sequence converges. I want to use this theorem here, the corollary here, that I want to show the limit of each of the p-adic norm of each of the term goes to 0. So let's look at the nth term here. What it is that this is p to the n over n factorial. So what's this p-adic valuation of this guy? So there are two parts. This is the p-adic valuation of p to the n over p-adic valuation of n factorial. Oh, excuse me, what am I writing? Division goes to subtraction. Okay, so this is equal to n. Of course, the p-adic valuation of p to the n is n. And minus, what about n factorial? Well, let's sort of do this calculation over here on the left. You have 1, 2, dot, 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 and then go to n. You multiply all of them together. You ask how many factor p's you can pick up from here. Well, let's see. So how many multiples of p are there? Basically, there are n over p of them. So maybe let's just let me just do a rough calculation. Because I'm a little bit running out of time. I don't want to sort of be too much rigorous, but you can make it rigorous, of course. So basically, roughly, every p of them will be divided by p, n over p. And what about multiple of p squared? Every p squared of them will be divided by p. Okay, minus p squared. And then how about multiple of p cubed? You have n over p cubed of them. And then all the p elevations are basically just sort of all of them. Maybe I should say add all together. So that's the p-adic value of n factorial, roughly, in a very vague form. But this is sort of a geometric series, you know. This is n minus. If you sum them up, this is just basically n over p minus 1. And of course, my p, I choose my p to be greater than or equal to 3. So therefore, this will definitely go to 0 as n goes to infinity. Excuse me, goes to infinity as n goes to infinity. And if p-adic valuation goes to infinity, then its p-adic norm will go to p to the negative infinity, right? Which is 0. Therefore, as you write down this sort of infinite sequence like this, all these terms, as n gets larger and larger, it's not only its real, I guess not only its real absolute value goes to 0, but also sort of p-adic valuation goes to 0 in some sense. This infinite sequence converges. So similarly, you can run the same argument if you have exponential pa. That's just 1 plus pa plus pa is where a is in a is in zp. This also converges as well. Same argument. And even better, we can do this following cool thing. Remember that if I do exponential x plus y, I can expand it as this. But on the other hand, this is same as this. So this is a formal equality here. And as you have sort of these p-adic sequences converging things, so you have exponential pa times exponential pb equals exponential of pa plus b. So here's a theorem. It's that, oopsie, a PZP. If you consider addition, think of the PZP as an additive group. The exponential map will always get you an element in something looks like 1 plus PZP, because you see that what you see over here is a 1 plus PA, and all the other powers are at least divided by P. So it belongs to here. And then it turns into the addition on this side into the multiplication on the right-hand side. It turns out this is an isomorphism. Excuse me. It's an isomorphism of groups, or topological groups, maybe. And the inverse map looks like I'm running over time a little.
Maybe 1 more minute, Liang.
Okay, 1 more minute to give you the inverse map. So the inverse map is so-called log. It's something you would expect what it is, right? Log of 1 plus PA. What it is again, right, Taylor expansion. But it's basically by the same argument, this converges as well. And you know that somehow these log function and exponential function are somehow formally inverses of each other's. And now because these are all convergent sequences, and therefore if you plug in these things, they would automatically converge. So therefore, we proved that these two are isomorphic. So let me let me state a theorem. Just 1.5 minutes. State a theorem that I'll prove next time. Is that I want P to be greater than equal to 3. That I want to give a structure. I said I want to give a structure theorem of this multiplicative group. And I want to say this is the same as Z mod PZ cross times the part that's congruent to 1 mod P. It's a multiplicative group, both. And of course, the first one doesn't do anything. But because of the exponential map here and isomorphism we have here, so this is the isomorphic to just ZP with additive group. This is given by basically log function. And then maybe 1 over P. So I think yesterday, Keith, did Keith talk about this yesterday, about the Galois group, where the Galois group is ZP cross?
I did
make it more.
Yeah, I talked about like 2 power extension. Yeah, five. Yeah, like the 5 power cyclotomic extension. I don't think I wrote Z5 star, but yeah.
Okay. Anyway, so the Galois group of that power is Z5 cross or whatever. And if you really want to sort of something more concrete group structure, so that's what it is, via this isomorphism. So I didn't have time to talk about it today. I'll talk about it tomorrow of how to establish that isomorphism. I'll end here.